let's continue on the Chapter 12. I put a file about the homework problems on the iCampus for Chapter 12, Chapter 13. So I will keep looking up those numbers and put more and more of those numbers, those problems on the iCampus. Yeah, I have a place that you can submit the homework on the iCampus in the place called the assignment. So try that. If you have some problems, let me know. Okay, any questions about those calculations we did like last night? So if no questions, let's continue on the colligative properties. The colligative properties are those kind of property of the solvent that has been changed by the solute you put in. And then those colligative properties, they're changing. How much they change? It only depends on the number of solute particles in your solution. So therefore, we are going to calculate, what we calculated in those previous sections will be very useful. Then to make the study a little bit like easier, we will classify those solutes according to their easiness of vaporize or not into volatile and non-volatile. And we will also classify those solutes into electrolyte and non-electrolyte. You study those concepts, electrolyte and non-electrolyte in Chem 1. Right? So electrolytes are those substances. When you put them in water, produce solution, the solution you get conduct electricity. Why you have to emphasize your solute is volatile, non-volatile, electrolyte, or non-electrolyte. The reason is those colligative properties depend on the number of particles in it, and then if you have those particles in it, they are volatile, and they will change your vapor pressure. If they are non-volatile, they will lower your vapor pressure. And if you put those electrolyte in it, and then the number of you put in depends on how much they ionize. So you think you put in like 1 unit of NaCl, but NaCl once get into water separate into 2 ions, then the colligative property will depend on how much ion you have. It does not depend on whether you have positive ion or negative ion. So this is from this theory you use those kind of common cross, and you have this 4 type of solutes. Okay. So you can have volatile electrolyte, not a common volatile electrolyte, like HCl. So HCl like dry gas, and you can put it into water. Once you put HCl in water, that become acid, that ionize, become H+, and chloride. then you think you put only one unit of HCl, but actually you get two solute particles. And so then, because it's volatile, and it can vaporize. So therefore, when you calculate the vapor pressure of the solution, you not only have to consider the vapor pressure from your solvent, like water, you have to also consider the vapor pressure from HCl. And if you have those volatile non-electrolyte, so this one we just talk about that. And next one is this. If you have those volatile non-electrolyte and the volatile, for example, methanol, and you put in water, and then the total pressure on top of your total vapor pressure on the surface of your solution, if you want to calculate the total pressure, you will calculate some of the pressure, the vapor pressure come from water, some of the vapor pressure will come from methanol. Methanol is even easier to vaporize than water. So that probably will make your vapor pressure on the surface of your solution is higher than the vapor pressure on the surface of pure water. And so we have other ones. These two guys. So these two guys are those non-volatile. Non-volatile, that means they will not vaporize that easy. But according to once you put them in the water, they can also ionize, or they cannot also ionize. So we have the so-called electrolyte and non-electrolyte. So for example, electrolyte and non-volatile is NaCl. NaCl, the table salt itself, not vaporize too much, right? But you put NaCl in water, so the NaCl ion pull apart by the water, and how much you put in, you have to be very careful to do the calculation. And for NaCl, when the concentration is low, you pretty much will get like 2 for each unit. So Na is 1, Na plus is 1, Cl1 negative 1. As the concentration increases, you might get a little less than 2. So we will have those called the Hoffman factors, so we can calculate in reality how much they really become. And the other one, non-volatile, non-electrolyte, like glycol, ethylene glycol was the total name. I mean, I think when we see glycol, I mean ethylene glycol, there's some other glycol, but so like the glycol, you know, when you put it in your radiators, that is coolant, and so so that is non-volatile, right? That's the reason you put it in, because otherwise your radiator become feel more pressure. And also non-electrolyte, because glycol pretty much 2 alcohol functional group on like 2 adjacent carbons. So you put them in, and they will not become ions, so they still are intact together. But so then, most commonly, we will have these 2 types. So in this chapter, most of the problem we will see the calculation is about this non-volatile. And then when you have those non-volatile, you also have to consider carefully, see are they electrolyte or non-electrolyte. Okay, so on adding a solute to a solvent, the properties of the solvent are modified. Few interesting properties we are going to study in this chapter are vapor pressure, and we are also going to study the boiling point elevation, and freezing point depression, and osmotic pressure. Okay. Now, the vapor pressure can increases or decreases, okay? And But we first, as I said, we are going to concentrate on the study of those non-volatile solutions first. If you have those solutes which is non-volatile, no matter they are electrolyte or non-electrolyte, and because they are not going to vaporize too much, like NaCl and glycol, so you put them in the solution, in the water-produced solution, and your vapor pressure of your solution will be lower than the vapor pressure of the pure solvent. So because of that, and we can have the melting point decreases. I will show you the phase diagram, and you can see from the phase diagram, because of your vapor pressure is lower, that means your total vapor pressure of your solution is lower. And then you will see the freezing point decreases, but on the other end, the boiling point increases. And then, if you put those solutes in your solvent, and you are creating those osmotic pressure. Okay? Because once you have the solute in, you get a solution which is not a pure water anymore. Okay? So for example, if you put those solutions nearby or come in contact with pure water, if you have some of those boundary or memory that can semi-transparent, transfer, that means the water can go through, but not those solutes, then you will see those kind of solution produced, or so-called the thirsty solutions. So you will suck in the water, and therefore they are going to increase the volume. And if you want to stop the increase of the volume, you have to apply some pressure. So the pressure you need to stop the increase of the volume for the osmotic pressure. And all those properties, we call them all those changes in the properties precisely, they're called the colligative properties. And colligative, these words tell us those change of those properties. It depends on only it's difficult to see. Depend only on the solute particles in your solution, or you can see the relative particles to the solvent or the concentrations. It's not depend on the kind in some sense, but we already specify our kind has to be non-volatile. Okay, first let's see the vapor pressure. Okay? And we still talk about those non-volatile solutes. Okay? If you compare your solvent along, pure solvent on the left side, so all those blue dots are solvent particles, okay? And there's no other substance in it. So on the surface area is all taken by the solvent. Right? Now vaporize is different than boiling. Vaporize, that means you can change from liquid into vapor, and that changing process before boiling can only happen on the surface of your liquid. Once you start boiling, then your process of changing from liquid to gas is everywhere. Right? But before boiling, it can only happen on the surface. So therefore, how much surface area will decide what is your rate of vaporization. Okay? And so therefore, it will decide your vapor pressure. And if you imagine some of those spots initially was there taken by the solvent, then they were replaced by some of those solutes. So the solute take those spots, but they will not goes up to the vapor. So they will reduce your effective surface area for your liquid change into vapor. And that's one reason. And some other reasons, and not only they take away your surface area, and they might have a different attraction than the initial solvents. So you put them in there, even though those guys not on surface, maybe on the second layer of the surface, so they will pull your leg and try to pull you back from going into the vapor. Okay, so because of those reasoning, and we can see the vapor pressure of a solution of non-volatile solute is lower than that of the pure solvent. And we can even use a formula or equation to calculate what will be the vapor pressure of the solvent over the solution. Okay? And if your solute is also volatile, you can also use this similar formula calculate the vapor pressure of your solute. That makes sense? So you can use the same formula, calculate the vapor pressure of every component that is volatile in your solution. Right? And your total vapor pressure on the surface of your solution is should be the addition of the sum of all the components. Okay? Now if you have water which is volatile, right? And then you have NaCl, which is non-volatile. Then you want to get the total vapor pressure of your solution. You only have to calculate the vapor pressure of the water, of the solvent. And you see the formula is reading like this: vapor pressure of solvent over solution equals mole fraction of solvent plus vapor pressure of pure solvent. Right? We learned yesterday how to calculate mole fraction of one component in the solution. Maybe you can calculate in the mole fraction of solute, and obviously you can also calculate the mole fraction of the solvent. Right? So that one is kind of temperature independent. Right? But the vapor pressure of pure solvent is temperature dependent. So therefore, usually you will specify. The problem will tell you at some temperatures the vapor pressure of the pure solvent is how much, and tell you some other information, and I want you to estimate or calculate what will be the vapor pressure, maybe just for simplicity, just use the vapor pressure of your solvent. And then if you know what is your solute, you will see that maybe also the vapor pressure of your total solution. If you write in those variable format, and you see this is P solvent, P solvent, and equals X solvent times P0 solvent. And obviously you can imagine the variable with the name, right? So that the P solvent is the vapor pressure of the solvent over solution. X solvent is the mole fraction of the solvent, right? And this P naught solvent is the vapor pressure of the pure solvent. And it now seems to make sense. The vapor pressure of H2O over a solution depends on the number of H2 molecules plus solution molecule. Right? So it depends on how much water in your solution. You can think about vice versa. Usually you think about how much solute. Right? And how much solute in your solution also depends on how much solvent in your solution. So these are relative relations. And you can see this P solvent proportional to the mole fraction of solvent, proportional to X solvent. So we talked about the ideal solution before. The ideal solution is one where the property depends on only the concentration of the solute. And as a particular example, an ideal solution is one that obeys Rauter's law. Like that. Okay? And if you measure the pressure of, for example, water in a solution that from glycol, and you can also measure like the or calculate the mole fraction of water, and you can see, you can compare your data from your measurement with this equation's prediction. You see, if we fall on the same line, and then you see your solution is ideal. And this equation is very simple. It's a straight line. It's straight. Because the mole fraction of solvent XA is always less than 1, so therefore this PA always less than PA naught. Then we can conclude the vapor pressure of a solvent over a solution is always lower, no matter what is your solute. Okay? But your total pressure, your total vapor pressure over the solution, sometimes not only from the solvent, it might also from the solute. Okay. So even though this is always true, your vapor pressure of the pure solvent is always higher than your vapor pressure of your solvent from a solution. This is the opposite way. see the usual way. So this is your solvent in solution. The vapor pressure of your solvent in solution is always lower than the vapor pressure of the pure solvent, but that does not always true or guarantee your total vapor pressure of your solution is lower than your vapor pressure of the pure solvent, because you might have those solutes which is more volatile, more easy to vaporize than solvent. For example, is methanol. If you put methanol and you put it in water, you can smell that, and then anyhow, you know the vapor pressure of the solution, total pressure is higher. Okay, so let's use this Raoult's law and do a few practice calculating those vapor pressure change of the solvent, and that might be also the vapor pressure change for your solution. Okay. So this example is assuming a solution has a solute this much of glycol, and you know glycol is volatile or non-volatile? Non-volatile, right? Non-volatile. So therefore, you don't have to worry about the vapor pressure contribution from this solute. I think this problem we saw before. We have those glycol, we have the water, and we know how to calculate those concentration units like mole fractions, right? And then just straightforward, you're going to use the formula and calculate what will be the vapor pressure of water over the solution. We don't even ask to calculate the vapor pressure of the solution. And you just say that you call that P820 is the vapor pressure of water from the solution. That's for equals X, H2O, then you know X means mole fraction. Okay. Then multiply by the P naught, H2O. And then just remember the P naught means the vapor pressure of H2O in pure format, a pure H2O. So you have that it gives you your 31.8 mmHg. So therefore you know this number, 31.8 millimeter mercury. The only things we need to find out the mole fraction of water in this solution. Okay? And so then you can see X H2O. Remember the way we calculate mole fraction, right? Mole fraction of H2O equals what?
The total mole is the moles of water over the total mole?
Yeah. So the mole of H2O over total mole of solution. Okay, now how do you find out the mole of water? You can find it from the gram. So we put 250 point here, gram of H2O, and from checking when we learn those conversion fractions, 1 over 18 on O2. Okay, now divide by the total mole of the solution. That means the mole of every component together, and this probably you still have this 250 times 1 over 18.02. Then plus what? And then plus what? The first one you take 250 divided by 18.02, that was the mole of what? 1 plus 1. 1 means 1 what?
1 mole.
1 mole of glycol, right? And how do we know 1 mole of glycol? Yeah, it tell you. So this not tell you is deriving 1 mole, but tell you have 62.1 gram, right? So that's just say 62.1, and then you have this 1 over 62.1. So similar format, calculating the mole of glycol. We have 62.1 gram of glycol. Okay? Then we'll divide by the 62.1 gram. Any questions? Anyone get a number of this? What is the number? For the mole fraction? Yeah. 0.933 and 3. Thank you. So then you will continue, let's say this is the one we used calculating the mole fraction. So you can continue on the second line. 0.93 and 3. And this that change into multiply, I mean multiply. Right? What do you have? You multiply 31.8 by 0.933. $29.6, for word 1 is the 7, right?
I think it was.
Yeah. 29.7. Unit, millimeter Hg, mercury. Alright, so this is relatively similar. Any questions? Yeah, 29.7. Okay. Okay, now let's see, you can change the format a little different. That means let's say for a 2-component system where A is the solvent and B is the solute. And you can see the vapor pressure change of your A, or vapor pressure lowering of your A, it will equals XB times P naught of A. So depending on what you really want to calculate in like right away. You want to calculate like the vapor pressure of the solvent, or you want to calculate the vapor pressure change. So that's all like makes sense. That means vapor pressure lowering is proportional to mole fraction of the solute. So how much vapor pressure of the solvent gets lowered depends on how much solute you have. So the more solute you have, and the more lowering you get. And so this vapor pressure lowering that will help you to understand those melting points and boiling point change. will help you to understand the melting point and boiling point change. Usually we're interested in like calculate or examines boiling point elevation, freezing point depression, means boiling point getting higher, freezing point getting lower. And you can understand that by examining this phase diagram we studied in Chapter 11. Right? You can see the blue line. Now concentrate on the blue line. The blue line representing the pure solvent. Okay? Pure solvent. And then let's see the red line representing the solution. Right? For those non-volatile solutes, you can have this kind of relatively position. That means your red line is lower than your blue line. Because for those non-volatile solutes, right, and they will not vaporize, and you can still only have your solvent vaporize, but some of those surface area is taken by the solute, or the solute have a stronger attraction to the solvent, so that make your solvent pressure getting lower, and you're supposed to have the total pressure or the solvent pressure plus the solute, but the solute will not contribute at all, right? Therefore, your vapor pressure of your solution getting lower. If you have some of those, it makes sense. If you have some of those other solute units, for example, if you have a mixture of methanol with water, and you measure the boiling point, and your boiling point is not elevated compared with water, you have a mixture, usually like your wine, your vodka, or your beer, your boiling point will be lower than 100. The pure water will boil at 100, but if you want to boil alcohol, you don't need 100. Right? That is the opposite. That means your red line will be the pure solvent, and blue line will be the solution. Right? For this case, and we have the non-volatile solute. Right? Now, because of that, actually we still we still want to examine our normal boiling point and normal freezing point. Right? Normal boiling point, which means your vapor pressure of your liquid will equals 1 atm. Right? So the vapor pressure must equals 1 atm and to boil, for your liquid to boil. Right? And then how can you make your liquid boil? You have to increase your vapor pressure of your liquid until 1 atm. And how you increase that? You usually increase the vapor pressure of your liquid by heating up. Right? So you will change the temperature like you see here. Temperature in this axis going from left to lower to the right getting higher. Right? And then you can follow the line that as your temperature go to the right, your vapor pressure getting higher and higher. Right? It must high enough to 1 atm, then your liquid will boil. Okay? Now, if you don't have a solute, you don't have those non-volatile solute in it, and let's say for pure water, you increase your temperature, so your pure water vapor pressure getting higher and higher, you feel that sometimes in the humid day, like today, like you feel very, very humid, that means there's a lot of vapor pressure, water vapor in the air. Right? And you increase, until you have this 1 atm, and then your water will boil, it will be vaporized everywhere. Then you see what is the temperature. When you go down, you see the temperature here. Right? So this will be the, let me like mark this. Right? And this was the boiling point of the pure solvent of water. Another call that, so TbH12. So that's TbH12. Right? If you're adding something like those non-volatile solution in your water, glycol, or you have those, let's say, sugar water, that's like a table of sugar, right? And then you measure the water pressure, your water pressure will lower. So the solution as a whole. But you still want to boil your solution. You increase temperature, and if you increase the temperature as normal place, like 100, you have here. And here, it's not 180 atm. So you have to keep going, increase more temperature. And so then, you will increase to here. Yeah, I have red. So therefore we will have the. So here, not red. So here, right? We'll call this TB solution. You can see, compare this TB solution, this red temperature with the other temperature. Obviously, our temperature increases, getting higher. Now, to understand the freezing point depression is similar. So because of this shifting, see this shifting, and that will also shifting the other line. The other line kind of goes up. And so this line here, this is the line that is the melting of the freezing line. This is the boundary between solid and liquid. Right? And so then that also depend on like the temperature and depend on the pressure. And let's say like before we have the solute in it, and to melt our solid, and you have to have this line, and that is at some temperature, and at 180 atm. And so at that temperature, your 180 atm pressure, and this is the place you will see you will have both state or both phase coexist equilibrium. And then you see the similar reason. So let's say this is our TF solution. The TF solution, and let me change back into the other one. So this will be our TF H2O, and that will clearly show you the freezing point of the solution gets lowered or gets depressed. All right, so. Then we can use like two very simple formula to calculate how much it gets increased and how much it gets decreased. Okay? Both of these two formulas have the similar format. And you want to see how much your boiling point increases, you use the first one. And then in the first one, you have the Kb, okay? And you have the little m. In the second one, you have the Kf and the little m. So you know how to calculate the little m, or you know what the little m is standing for. What the little m is standing for? Polarity. Okay? And we'll see this little m equals mole of solute divided by kilogram of solvent. Right. So that you have to emphasize, even though in the formula And you did not see that those notation little m, but I think little m just means the little m for the solute. Yeah.
And in a test, how do I know that this is a mass, like Martin mass or molarity? I don't know. Because like, yeah.
That's a good question, yeah. So you will not know the mass or not. Depend on the situation. depend on the problem. If you see like if I give you a question, ask you to calculate the boiling point increases, the boiling point or the freezing point decreases, and you know that is not mass, right? And but you will use mass to get the little m. Right? So I'll give you like in the last example 62.1 gram of glycol, right? And then you have to use the molar mass to find out the mole, and then you find out the kilogram of the solvents, and yeah.
But then like since I studied in French, like this is like mass, like when you put m, so like when I see that, theoretically my mind is like mass, nothing else.
Yeah, because you think you are still like you are not French. Yeah, those are the like the metric system, right? Yeah. Now let's see one example. This was the same problem we saw before, like C2.1 gram of glycol and 250 gram of water. So you have this, and what was the boiling point? So what was the boiling point of the solution? And now the question you have to also see, like it's interesting to ask what you want to calculate. It's not only calculate the boiling point, the increases or the freezing point decreases. Now this question, like all those, you have all those criteria. So you have to have the non-volatile solute. Okay, so you first calculate the delta B. Okay, so what is delta B? For delta B, you can think about there are two formulas for delta B. Okay. Now let's just write our formula from the last slide. Okay? So delta B will equals the Kb times what? Times molarity. And then the Kb gives you, right? And the only problem is how do you find out the little m? I think we also did this find the little m like previously in some of those examples, right? Now let's do it again. Okay? So little m will equals. Now this time I tell you is 1 mole, and so then you will divide by the kilogram, right? You will get 0.250 kilogram. You know like where I get the 0.250 kilogram?
Oh, you multiply it by, you just converted it.
Just converted this 250, right? Multiply by 1 over as a solvent. And so this becomes 4.00 liter m. Okay. Or you can see, if you want to be consistent in what it gives you, you will use what gives you. So this is like the 4.00 molar or molar. Then just go very straightforward. You have this 0.512 degrees Celsius over MOLAL. This is given. That's the constant. Right? And this is the characteristic number for water. Right? This is the characteristic number for water. So for different solvent, you will have a different number of Kb. You might have a different number for Kb, for example, for ethanol, right? Or for benzene. We talk about ethanol or methanol as a solute, but obviously it can also be solvent. Right, and so now we multiply by 4.00 MOLAL. So these two guys cancel out, right? And you get what? Times 4. 2 point something, right? 2.0, 2.04. And what is unit? Degrees Celsius. No, you did not finish the problem because this is only what? Yeah, you have to add. You have to add or subtract. Let's see whether we add or subtract, why we add. Okay? So that's what at the beginning I said this delta TB has two equations. So my equation is like that. Right? Now the equation is the definition. Right? Let's see the definition of delta TB. Okay? That means your TB solution minus TB what? That's our solvent is water minus TB water. Right? So that's the definition. What is your delta TB? Delta TB means your boiling point change. So you take the boiling point called the TB of the solution and subtract by the boiling point called the TB of solvent. And your solvent is simply water, and you see that's H2O. Now you use this equation. I think I might quickly, find out. That's just you know that add equation, so therefore you just simply take this 2.048 add on to 100. Right? Now if you don't remember that, you just say that 2.048 equals TB solution minus no TB water. That means the normal boiling point, right? So 100 degrees Celsius, and so that means you just adding 100 on both sides, and you get TB solution equals 102.048, like that. Okay, any questions? Okay, so 102.05, because we have to keep the right number of sig figures. Calculate the freezing point. Now this time we calculate the freezing point of. Now this time we already know how to practice calculating the little m, and then we can just you can just, we don't have to do that, we don't do that calculation, we just straightforward using the formula. So we have delta TF, and then we equals KF times little n. Okay? Now let's just 1.86 degrees Celsius, and keep doing like straight. Okay? And times 4.00 MOLAL. And MOL comes out. Am I right? So this amount of degrees Celsius, right? Right. Now the second step, you have to go by the other definition, delta TF. Let me just clarify so that definition. So this definition of delta TF, which means your TF of your H2O, and then minus the TF of a solution. Alright, and then just like you just find out 7.44 for that, and 0 for water, and then minus the TF solution. Alright. So then your TF solution equals negative. I hope that's right. 7.44, right?
Yeah.
All right. Any questions? Any questions or comments?
Is that negative 7.44 or positive?
Well, depends. The negative 0.44 is the result for the so-called freezing point of solution for this line. And positive delta 7.44 is for this delta. So that means how much your freezing point gets lowered, your solution compared with your solvent, is that much positive number gets lowered.
So if we're going to do the dot formula, we just make it a negative after we get the answer.
You depend, because this one you have a 0, you can just make it a negative. If this is not 0, you pretty much have still remember those kind of equations. If I want you to calculate what will be the freezing point for a solution, and your solvent is benzene, then you will have this number not 0.
Okay, so only if it's H2O.
Yeah, only H2O you can do it very quick. So then you can just say H2O, then become, because it's 0, it just become negative. If you want to see the boiling point, you just add in like that number to 100. So what was the other question? Okay, now usually that's two calculations, not that difficult. Maybe at the end, and once you get those delta something, delta TF or delta B, you have to think carefully which way you go. Okay, you always think this two way. Okay, and if you adding or subtracting, you get some number doesn't make sense, and then you just change. Okay? You know your freezing point of the solution should be lower. And you calculate maybe water is your solvent or maybe benzene, and if I give you benzene, the freezing point like is some numbers, okay? And let's say is positive 17, okay? And then you change, you calculate, you find out your freezing point, those solution of benzene that has like something glycol in it, and then make it like your freezing point become like 27. And then you know that doesn't make sense. You instead of like adding on the 10, you are subtracting the 10. Alright, so that is the difficult for that program. And so then this type of program, which means you want to find out the molar mass from the boiling point elevation, or from the freezing point depression, or later on from the osmotic pressure, that is even little difficult. Okay? So this is even little difficult. And I can see it works. So a solution prepared from 1.25 gram of oil winter grain in 99 kilogram of benzene, yes, that's benzene, right? And see the boiling point of benzene is 80.31. Determine the molar mass. Oh, excuse me. The solution has 80.31. The boiling point of benzene Q1 is 80.1. All right. So read the question carefully. Note like don't like mix up those numbers. So you want to calculate the molar mass. Okay, I remember I did, because this kind of difficult problem, so I will usually for those difficult problems I will give you the steps. Okay, and so now let me give you those steps, and then we'll do the calculation. So when you have those colligative properties, you can use them to measure like your molar mass of your solute. Okay? So what do? You will first use those colligative properties, maybe osmotic pressure, maybe vapor pressure lowering, maybe the boiling point elevation, or the freezing point depression, to find out your solution concentration. Okay? So now you know like in all those you have the solution concentration. Remember that? Okay. So first, let me rewrite on top. 1, find concentration. 2, find mole. Okay. 3, you will take a gram divided by mole. Find the molar mass. So now I will erase those steps, okay? And then we can do the calculation. Right? Okay, so first let's get familiar with these 3 steps. Is the first time you feel like strange, and after a few times you are repeating these 3 steps. So all of the program, same as 3 steps. First, find the concentration. Okay? The concentration may be little m, maybe capital M, maybe more fraction. So from those concentration you find out, and usually there's some other information given to you. Concentration is the ratio between solute, and most of the time is the ratio between solute and solution. Sometimes is the ratio between solute and solvent. Right? So if you find out the concentration, which is the ratio, okay? Solute, let's say over solvent. If you also know the information about how much solvent you have, so therefore you can just multiply after you change the unit and get the mole. Once you have mole, you know the molar mass is a gram per mole. Right? That means you will take whatever the gram, and assuming that gram, imagine that mole. Right. So now let's go in these 3 steps. First, let's find out the concentration. Right. So let's first find out the concentration. The concentration, what concentration you have, depends on what property gives you. Okay? Now this problem, what property gives you? Is a freezing point, a boiling point, or vapor pressure, or osmotic pressure. What property gives you? Boiling point. Okay? So therefore, you can think about using that delta TB. So you will say delta TB equals KB times little m. And little m is not a mole, it's molar, right? If you want to find out the concentration, so in this formula, the little m is the concentration. So therefore, you say you want to find the concentration, that means depend on the property, what concentration you can find out. Because we have the boiling point property, so therefore we can find out this little m from this equation. And now, so little m will be our unknown, will be the one that we try to find out, right? We have to find out the other two. One is very simple, it's given to you. KB is given to you, right? So then you have to find out what is delta TB. Delta TB, you also be careful, like delta TB, what change to the boiling point? Is the boiling point increase, or is the boiling point decrease? Or is the boiling point increase or boiling point decrease? And boiling point for those non-volatile solutes, they increases. And you can see from this example, right? So your solution's boiling point is 80.31, and your solvent is 80.1. Right? So you first say, I will first take like 80.31 minus 80.1, and this is the same as my delta TB. So I just do subtraction, find out delta TB, and this will equals 2.53, right? And degree Celsius over little m.
No, it equals 0.21 degrees Celsius.
Yeah. Oh, I see. But I did not do the calculation yet. I just substitute. So you just go straight forward, and something on the left side, see on the left side, so something on the right side, see on the right side. And so then this, the other little m. And so this will be our degree Celsius. And you want to find the little m, just divide 2.53 degrees Celsius over little m, and divide this 2.53 degrees Celsius over little m. So on this side, this two guys cancel out, and you get the little m. Okay? On the other side, so this temperature cancel out, and then your little m will flip on the top. And obviously your little m is equal to little m, but just equal to how much little m, right? You still have the same unit. And you are right, you will take this 0.21 divided by 2.53, right? And that will give you what?
0.083.
0.083. Okay. This is the concentration you find out. Okay? You see, in this solution, in this bending solution, with some of those winter grain of the method like silicate, right? So some of those non-volatile solute in it, and you find out how much solute in it is this much, which means you have 0.083 more of the methyl silicate in one kilogram of water, or 1 kilogram of benzene. And what is our second step? We find the moles. So this is concentration. Okay? Now you rewrite, but this concentration is just a notation. So this is just a notation. You know this notation like little m, capital M. Okay? Sometimes you use notation. Okay? Sometimes you have to explicitly spell it out. Right? So you are starting from like 0.083 mole, okay, over 1 kg. 1 kg in this example, 1 kg solvent, and our solvent is what? What is our solvent in this example? The benzene. You will write like 1, let me just abbreviate benzene. So 1 kg of benzene, right? And right now this is a ratio. So this is a ratio. You have number on top, number at the bottom, and number bottom is 1 kilogram. Okay? You want to find out, in your solution, exactly how much more, not how much more per kilogram, just how much more. Okay? You have to count out the kilogram, right? You count out the kilogram. Okay? Do we have any information about the benzene and the solvent? We have 99.0 gram, right? And so what you do, you can just let me just use this. You know how to convert like 99 gram into kilogram, right? So I assume you know how to convert very quick. Let's just use the result. So what is 99 gram in kilogram? Yeah. So it will be 0.099 kilogram benzene. Right? So then, see this kilogram benzene, the unit comes out, and you will get how much more? I omitted the more of the solute. Right? But you know the more of the solute. Now this is very like straightforward. So what is the calculation? What is the result? You forget 0.00 something, right? 0.00082.
No, just 2 zeros.
Oh, okay, there are 2 zeros. All right, so that. Alright, now what is our next step? Yeah, so next, gram or more. Okay? Now you think about, you find out this much more of your solute is in that much solution. And that's from your calculation. Okay? So you don't know like what is how much more in solution, but somehow you find out if I have 99 grams of those solution with those kind of freezing point, I find out we have this 0.0082 mole. You can now you have 2%, okay? And you play those puzzle game, okay? So you find out how much more. Then I will tell you. Instead of that amount more, I will tell you actually I put in that amount of gram in it. And then you say, okay, so that amount of gram is same as that amount of more. So therefore, you take the gram and divide by the mole, that will make sense. So therefore, 1.25 gram divided by, let's see this unit mole, right? 0.0082 mole. Yeah. Okay. 300 something. But I know the unit should be gram per mole. Right? Yeah, so that's those are typical problem. I think if inside those problem, I will do like a few examples, a few practice. Okay, what do we get?
152.4.
Huh?
152.4.
152.4. Is that right? Okay. Yeah, 152.1. Alright, let's do a practice. You follow the 3 steps. Try to get the three steps. Try to first find the concentration. Any progress? Any idea? What do you find? I don't have my calculator. What's the approach? about the freezing point, right?
Yes, around here.
Freezing point is charging, very good. So even though given negative freezing point, so it becomes delta TF equals, and 1.9 so you divide with little n. Good. Then to find, so that's the first step, right?
Right.
Result of
Yeah,
the
that's
first
number
step, number one. Number two, you are going to find the mole.
So this is a, this equals
Use that way, yeah, use that way. So good.
under the wall,
Yeah.
so then this is the wall.
The mole, that means you take this number times this, right?
Yeah, and then you take this number and you take this random sum.
Ground story. Sometimes you this step will be very become a little complicated depending on whether the solution is electrolyte or non-electrolyte. So for these two problems, last problem we talk about the wind and rain, which is those guys are not electrolyte. So therefore they are not going to separate.
Okay.
And this I tell you is non-electrolyte, so you don't have to worry about separate, right? So you will take, so that will get you straightforward by the number, the more you get. And, yeah, that's one. So you take 12, right? 12 divided by 0.083, 124. Good. Well, you get, let's follow step by step. So first step is finding the concentration. Right? Okay, that's this delta TF. You have to find out delta TF is the depression. You have to take the freezing point of the pure solvent, okay? Subtracting by the freezing point, yeah, and then you are. You first, so that's a two equation for the delta TF or delta TB, right? So the definition of delta TF is the freezing point of the pure solvent. Okay? So as is the one equation for delta TF is TF of yeah, very good. Yeah, very good. Yeah. What do you mean? This is TF. TF, what is TF of what?
The freezing point, right?
Yeah, freezing point. But this number freezing point of solution, right? Freezing point of solution is negative. What is the freezing point of water? Zero. You try to draw to keep it this, starting on the second one. Yeah, you can do that, but this will not negative. Not negative. This is the freezing point of the solution. Okay? Then, according to one problem, we said delta TF. It probably you have this equation for delta TF doing those calculations for those from those information. Then there is another equation we call the definition. So that means delta TF equals for those like freezing point of depression process. Well, we will have another equation was delta TF equals like a TF of pure solvent minus the TF of solution. So if you use that equation, you might know what I said here. So this delta TF equals TF, not TF like that, solve, you can see solving, and minus TF solution. So that's another equation. You have this equation, you have that equation. So sometimes you have to use this equation to find out this number. And sometimes you use this equation to find this number, then you put it here. Okay? So depending on what we know, so now we can use, because this in this problem gives you this. So you can just say what is this one, you see what the solvent is what? 0. Yeah. 0 minus, yeah, that number is negative, right? Negative, negative. Yeah, yeah. Okay. Then your second step is you are right. So you are taking this positive number, right? The 2, you are saying you have this is a little m, and little m is concentration. Yeah. So that means let's find out the number first, right? You can do that everything. And this step can rewrite 104. No, 104 you can change the little m into 4. Yes, or 1 kilogram.
Delta TF of water minus
You spread it out. You just spread it out.
Yeah, okay.
You will spread out if this is m or n. You have to be careful, so you have to convert it to gram over what, right? Yeah, also write it out, because this is 1 kilogram of solvent. No, 1 kilogram of solvent. The solvent in this number is what, right? And so let's say, do we know? Yes, yeah. And then you are going to, so right now you have this, here this number is already 1 kilogram. This is from the definition. So what you want to do in this second step is cancel out this kilogram of this. Very good, very good. And then you will just simply convert that 80, and that become, yeah, 108, you can write that out. Yeah.
What's up?
Good. You get that right, you get that right.
That's right?
Mm-hmm.
Okay.
You probably want to do a little better job, write out everything, because later on you can review. Don't do everything just in your calculator.
Okay.
Yeah. Any questions? You got a B, 144, right. Right. Anyone get some other, like 144, right? 144? Okay, 144. Get anyone down? What about you here?
Yeah, because I think better.
Yes, yeah. Okay, good. Anyone need help? Got it? 44? Alright, I think this problem right now is relatively like simple, right? This is 3 steps. And those last two examples, about those kind of solutes, we call them non-volatile and non-electrolyte. Okay? So therefore, in one step, in the last step, in between step 2, step 3, you do very simple. You find out the mole of the solute, and you just go directly use that mole divide into the gram of the solute. Right? So in this example, you find out 0.0083 mole, right? Or 0.083 mole. You take that mole divide into 12 grams. Okay? Because those solutes are non-electrolyte. That means you have that amount of gram in it, and you produce some more, so those more are straightforward. You did not like really separate like one unit into 2 units. If later on we know like some of the problem that is not this kind, is electrolyte, and you have to multiply your equation by so-called I, okay? Which will tell you how much unit you get from one unit. Osmosis are those kind of process you saw before on the first slide of Chapter-12's lecture notes. And that's it because the nature's tendency always try to be uniform. If you have some area, your concentration is higher, your water amount is lower, and some other place there is more water, then this place that has lower content of water going to suck in the water. I mean then assuming you have some of those blocking, because otherwise you just everything mixes together, right? Osmosis. So that is the process we saw in the last slide. Those eggs. So because of those kind of separations or the boundaries, and you will have this osmosis possibly can happen. In a biological system, most semi-impermeable membranes allow water to pass through, but solutes are not free to do so. So in a biological system, like I think a lot of you like major in like health science, maybe want to be a nurse, or maybe want to go to medical school or dental school, right? So you will see those in the hospitals. You give those patients some of those IV or some of those injections, some of those fluid, and you have to worry about those osmotic process. Okay? So you not only give them some of those nutrition, and you have to say like balance the nutrition with water. So this show you the process, and you see you have to use some of those pressure to stop this process of like let's say the migration of water from one side to the other side. Okay, and you have also a formula to calculate what will be the osmotic pressure. Okay? The equation for that is very similar as the equation you studied in Chapter 5. Remember in Chapter 5, we have that ideal equation, ideal gas equation. Yeah, ideal gas equation is PV equals nRT. You just change the variable. You change the P to pi. Okay? Then you divide the V out from the left and onto the right. So if you do that, you get m over V. You get m over V. Anyone see this? And you know n over V. N over V. What is n? Mole. And then we know in the ideal gas equation, V is liter. Right? V is liter. Remember the P is ATM. Volume shall be liter. The volume shall be liter. And if you have these two units, then you will see this R will have this, or I will have the number here. No. So I will see the R is so your R has this number and there's a few units. That is L, right? So that's liter, and that's that. Now, a few kind of confusing names. So a few confusing names. One is what is sort of the isotonic? Tonic means pressure. Isotonic means your osmotic pressure are the same, right? And obviously you can see from this equation, you want to have the same osmotic pressure, and you should have the same M. So right now we're still doing kind of just straightforward. So the capital M is more over liter of solutions, and you don't have to worry about whether this capital M will come from your formula unit or come from your the result of separating the ions, right? So those so-called electrolyte or non-electrolyte. And from that equation also, and you can see the hypertonic. Hypertonic, that means if you see this solution A is hypertonic to solution B, and that means your solution A have a higher concentration than solution B. Now here you compare the solution, that is so this is a cell. That's a cell, right? And then this is outside, right? So that means you compare two solutions: the solution inside the cell or the solution outside the cell. Okay? So I think for this picture, I tell you the solution outside have a higher concentration. If you have a higher concentration of the solute, you will have a higher osmotic pressure. And then the solution is more thirsty. So solution will suck out the water from the cell. And oppositely happen. Oppositely, you will see if your cell have a higher concentration, and then the solution inside the cell will have a higher osmotic pressure. And then relatively rigorously speaking, so the solution outside have a lower concentration, and their osmotic pressure will be lower. So as a result, those blue arrows, as I emphasize, indicating the direction of the solvent flow. And in a biological system, the solvent, the common solvent is water. I think the human body was about 70% water. And you can see this is three pictures. Normal cell, then some of the cell, those blood cells or some cell, kind of shrink, some other cells swell. But you can tell immediately those cells is in what kind of solution. The solution with a higher concentration, lower concentration. Higher concentration, hypertonic, and this is a hypotonic or lower concentration. So that's very good. Alright, so I think I just emphasize for picture A, there's an isotonic. Isotonic means osmotic pressure. Okay? And from that equation, that means your concentration are the same. Now, for those kind of for the biological system, your concentration are the same. That means the content are the same, right? That's why you're treating those like those patients when you go like as like a nurse or a doctor, and the cell, you still have to balance those osmotic pressure. Obviously, the human body cell have different content. You might have those protein or so on, and then you want to make the same osmotic pressure. You probably cannot adding so much the same material protein in your IV. You can add like sugar or salts and make the concentration similar as like as the cell. Hypertonic, that means you have a higher concentration of the solute, and as a result, the water will flow out of the cell. Okay, so the last one, and that means the concentration of the solution outside of the cell is lower. Right, so the similar, I think this is a similar procedure. So we talk about that equation, then we're going to do a practice using that equation first, right? So osmotic pressure of solution found by doing this, molar mass this, and it should be how much ATM. On this one, inside the equation, we call that osmotic pressure is pi. Understand? This pair will equals capital M and times R times T. The question asks you what is pi? So what is pi? So what is this? Now you have to find out all of those numbers. I think the number is difficult to find out in the capital M, right? R you should know 0.082006. To find the capital M, to make sure is all the particles in the solution. Okay? Don't have to be the molecular you put in. Okay? If your molecule put it in, don't do anything, just use the molecule you put in. Okay? So don't have to use that. But if you put in the molecule, your molecule change into ions, then you use the ions. Then how do you know? The program will tell you. If you have those solute, which is non-volatile, non-electrolyte, you can just use your calculation and see how much molecule you put in. So this is non-electrolyte. Okay? So we will just use the calculation, find out how much molecule we put in. So the capital M for equals mole divided by liter of solutions, and then we know how to find out the mole. Okay? I will make the calculation a little like quicker. So this is the gram of the solute. Okay? Then you will multiply by this 1 mole and 180.16 gram, and then divided by 0.250 liters. So one number gives you very straightforward. Tell you you have 0.250 liter. But the other number, we have to do some calculation. Okay? So why I put where I get the 0.025?
That's milligram.
A milligram. A milligram is our non-volatile, non-electrolyte this aspirin solute, right? And what is 180.16 gram?
The molar mass.
The molar mass. Okay. So those are the typical techniques we sometimes we need to review what we learned in Chem 1. Okay. So you take the gram and you can see you divide by the molar mass, or you see you multiply by 1 over the molar mass, okay, you will get the mole. Okay. But if I don't give you the gram like a derivative, you somehow you find out the gram. If I give you kilogram, you times 1,000. But if I give you milligram, you divide by 1,000. Right? Very good. So that will get the. So this will give you the capital M. molarity. Okay. Okay, what do you get, John?
D.
You want to find out the final answer, Nick? Oh, see, I think Nick is probably not right. I don't have the calculator. So what is the capital M? Yeah, the molar. 0.00.
Oh.
What is this number here?
Oh, I got 5.55 times 10 to the negative 4.
Okay. And this is what is the unit? More over what? Yeah, that's it. Right now we probably want to emphasize again more little solutions. Let me emphasize again. So here you take this milligram referring to this molecule. Referring to that molecule, the compound. Because that compound is non-electrolyte, so you take this number divided by this, get more. You don't do anything yet. Okay? You don't have to multiply this number by 2 or by 3. You just simply take that number divided by the liter of solution. Okay? Later on, if I give you solutes like NaCl, not aspirin, you will take the gram of NaCl divided by the molar mass of NaCl. For NaCl, each one NaCl give you 2 ions, give you 2 something else. So therefore, we can multiply that by 2. But right now, you don't have to do that because non-light. So make out that, and so now the next step, you just don't forget the temperature. You cannot use 25, okay? Because 25 is Celsius, right? Next equation is pi equals 5.555 times this, and divided by L, okay? And R shall be 0.08206 ATM times L divided by mole times Kelvin. If you write out all the units, and then you know all the units will come out, right? I will give you the final unit level will be right. And you can see this arrow comes out, right? And then more and more come out. Has should be pressure. Pressure should have the pressure unit, maybe ATM, maybe millimeter mercury. So right now you still have the K. Obviously, that means you cannot use 25 degrees Celsius. Means that is also metric system. So you will use 298 Kelvin. So sometimes I will probably just use a result as you get by using 25. Okay. So you come out of this, and so what's the answer? E?
D.
E is too big. So that's D. That's about ATM. But you can obviously after you get ATM, you can change into millimeter of mercury or whatever the unit like sometimes in those multiple choice. All right. Any questions? All right. So that's now. And I said that 3 steps. You can use different property. And what are the 3 steps? when I think about this program, when I on my way here. So what do you,
Find the concentration.
find the concentration first, and once you find the concentration, and from the concentration you find what? You find the mole. That's explicitly what is the mole. Okay? Then the last step, yeah, take the ground divided by the mole. So let's finish this practice. I want to take a break. Hemoglobin obviously is non-electrolyte, so therefore you don't have to worry about find out the mole, then multiply by some numbers or divide by some numbers. You have to change your way of finding a solution first, finding the concentration first, right? So in the last practice you did, you use a freezing point depression, find the little a, right? Now this time, the property you have is called osmotic pressure. And then you have to think about the equation for the osmotic pressure. What is the equation for the osmotic pressure, right? Very good. You use pi equals the Kelvin mRT, right? You just make sure you know the pressure should be ATM, right? Temperature should be Kelvin. And then your R is 0.08 to 0.06. This is the gram. Okay. Now you want to take the gram. How do you get the gram? Let me see the. So the first few steps seem to be okay. It's really not a many. 280 Kelvin, 298. 25 plus
273, right?
Then I use the R dog,
The R probably 0.08206.
Okay, and then this is the gram.
Now this, you have to find out this number first, then you find out this number, right?
I'm trying to match this number.
Yeah, this number is given to you, this is convert, kind of find out. This number given to you is is this number given to you? The path, the automatic pressure?
It's both, we gotta convert it to ATM.
Yeah, once you get ATM, you put ATM here, and then everything you know is you establish the capital M.
So we looking for this number?
Yes, so that's the first step. Because this number is concentration. So depending on the problem you do, in the last problem, then I say you write that out. So last problem, the property given to you the freezing point. And in that problem, you use the equation and find out the little m. The little m is still the concentration, right?
Okay.
Go ahead, just.
So
But this is the converting to ATM, you have 10.19, that's right. I think that's just 10.00.
Yeah,
Oh,
it's 10.
69,
You have to convert this into ATM.
And once I do that, can I move this over here and put this over there to find M?
This M here, you just divide this R and T out, you also divide R and T on the left side.
Okay.
So first convert the 10 mm HG into ATM.
I have it on that.
Okay, what do you get, Nick? Sorry, right, 64,000. Let's see your steps. You first use this into ATM, divided by 760, 0.0298 perfect. So get this capital M. Is more over 1 liter. The temperature over 1 liter is the same, right? It is 35. Exactly. Very good. Anyone get like 64,000 gram per mole? Yeah. Perfect. Like that. And yeah, so any questions? Let's still like summarize it. Summarize it so you have this 3 steps. Okay. First, you want to find concentrations. In this example, your concentration should be the whatever have something to do with the osmotic pressure, right? So which is the capital M. And the equation for the osmotic pressure is pi equals M times R times T. Most of you get that right, okay? But just be careful when you have the equation, use those variable in it with the right unit, okay? And the parameter here should be ATM. Okay? And now here this is the pressure, so this is pi. Okay? You cannot take this number right away. You will just first take 10.0 millimeter mercury divided by 760 millimeter mercury. Okay? For ATM, and that's not my usual way. I should write those conversion ratios. Well, this is not easier for me to do that. So write my usual way. So that means I will multiply by 1 ATM divided by 760 millimeter mercury. Okay? So these two come out, and what's the pressure you get? 0.0138. 133?
Just 1-3.
Oh, 1-3. Okay. Perfect. So this, now this has a unit ATM, right? And so then you have to know what is the name of R, right? R is a constant, okay? A constant. So that equals 0.08206 ATM times L over mole over Kelvin. And so then you just you know the T in Kelvin, mass in Kelvin. Okay. So therefore you will see that equals 25 plus 27.3, right? So make sure you don't simply use the Celsius and 298 Kelvins. Now you pretty much have everything except the Kelvin. That's perfect. That's the one you want to find out. Okay? You don't always know everything at the beginning, right? And otherwise you don't have the solid. And 0.013 ATM equals Kelvin M you don't know, and 0.08206. Okay? And now I will keep writing the unit. So this is ATM, right? This comes from the R, and then this, and then this. Okay? Unit, as you study like in Part 1, is kind of the so-called dimensional analysis. It's a guiding line. So if you keep tracking the unit, and not only you know what you did right, what you did wrong, sometimes the unit will give you some directions. And so here is 298 Kelvin. Okay. Now if I simply like cancel out something, make the equation a little simpler, see the Kelvin cancel out, right? Okay. Most of you also know you can cancel out the ATM here with the ATM, even though both of them are on the top. And here you cancel out this with this, one is on top, one at the bottom. You can cancel out both of them on the top if they are on two sides of the equation. Alright, so now the unit left over is this mole and this liter. Obviously, you know that you flip it over, right? And you want to remember out. So that means the calculation over here. What is the capital M? What capital M? What capital M you get? Yeah. So this is the value, the number.
I got
Number one.
0.0005361.
35161.
53161.
53161. 0.000, right? 30.
3 zeros.
Yeah.
Is it right?
Is that right?
That's what I got.
Okay. So then this number has what unit? You just flip over the more over liter. Are we right? Right. So this is
Because I rounded.
this one more, yeah, we
So you get roughly
didn't do this.
I
Okay?
don't think it matters.
I didn't know what to do after that.
This is the result of your first step. Okay? And you depend on the question given to you. If the question given to you is a freezing point, last one, you find the little m. Okay? So that means we have that much more in 1 liter of solution. We have that much more something, maybe ion, maybe molecular in solution. And make the osmotic pressure become like that. So then, if you have some of those electrolytes, they will divide, they will separate, right? So then you have to think about if you have this more of NaCl, right? You don't really need that much more of NaCl unit. I mean, if you have a solution of NaCl, you get this much more of particle from your calculation in 1 liter. You don't have to use this much more of NaCl. You only need half of that NaCl. But because half of that will sometimes will do something right. So you just divide this number by 2 or by 3, depending on what's the problem. Now for this you don't have to do anything. We'll go to the second step. Okay, any questions? Okay, now what do we do on the second step? So now we have this result. So this is concentration.
Plug it back in.
Right?
Plug it in.
Then you can think about flooding or whatever you want to find the more, right? So this is the M. M equals 0.000536161 more over a liter. Second, find what do you say? Find what? Yeah, find the moles. Okay. Find the moles of the solute, or the solute unit. You often have there and just liver away. Now here you have more over liter. You have to count out the liter, right? Therefore you have to know how much liter you have. Now here is per liter. This problem I just give you kind of soundly, I will say that's also 1 liter, right? If I give you 2 liters, that's straightforward. That means you have for 1 liter you have that much. You have to multiply by 2, right? Now here, it's the same, right? So you have so more 0.0053161 more over 1L. We don't use the X because the X sometimes confusing. So what you do is here is also 1L. 1L. Get it? So then you get the same number. Now let's change that into scientific notation to be easier. 53161 times 10 to the -4. Right? Yeah. And this is the result of second step. Right? So what do you do on the final step? So you want to find out the molar mass. Molar mass equals gram divided by mole. Do we have the gram? You probably, if you want to make a note of it, sometimes you don't remember gram of a solute. Okay? Gram of the solute you want to calculate. Okay? Yeah, but let me do that too, so you will have the same notes. Gram of solute, right? Divided by mole of solute. Now we have two numbers. We have 35.0 gram. That's a gram of solute, right? So once in a while you can make that. Right. So therefore you will get the result. You already
65,837.
okay. So that, yeah. So that's about it. So 6.5 times 10 to the 44. And the unit is G over MOL. Right, I think you are keep doing the practice, so let's take a break. Take like a 5 minute break.